Okay. So I really like this unit. It has a very natural flow to it. And this first section is all about inverses. We're going to use that word inverse over and over and over again today. And what I did was I kind of just prepared this first page of notes. Don't worry, I'm not doing like note templates or anything like that I don't provide you ahead of time. But I did want to provide this template just to show you what an inverse is. And an inverse is found by simply swapping the x and y in every single ordered pair you see. That's all an inverse is, everyone, is you just change the position of x and y. So if someone asked me to find the inverse of this relation right here, then that inverse is going to be 3 ordered pairs. And what's the first ordered pair going to be for the inverse? 2, 3. What's the next one going to be? 5, negative 4. And the last one's going to be? Negative 1, 6. That's how you find an inverse, everyone. You just swap the x and y in every ordered pair. Now I realize I've underlined most of that sentence, so it kind of loses its meaning. When you swap the ordered pairs, the other thing you're doing is you're swapping the entire domain and range. So the original relation up here has a domain of 3, negative 4, 6, and a range of 2, 5, negative 1. But when we write the inverse, it has a domain of 2, 5, negative 1, and a range of 3, negative 4, 6. If you swap every x and y, then you're also swapping the entire domain with the entire range. Now, of course, it's going to get a little more tricky, and it's going to get a little more difficult, and I'm going to add some more details as we go, and there's always a bunch of things little things we have to worry about. But that is the basic idea today. Switch x and y, and you got an inverse. So, do you think we could do that with a graph also? Yeah. This graph has an infinite number of ordered pairs on it, but what we can do is we can use the 3 key ordered pairs that I've labeled to get 3 new ordered pairs over on the inverse. So what would be one ordered pair that would be on the inverse for sure?
2, 4.
2, 4, very good. We have 2, 4 over here. What's another one we have?
1, 0.
1, 0. And what's the last one you know you have? Negative 3, negative 2. And then we just connect the dots to get all the other infinite ordered pairs that aren't labeled. And that's the inverse right there. We're done. We found the inverse. And once again, the domain and range do switch. Now this time, we don't write the domain and range as a list of numbers. We write it in interval notation, because there's an infinite number of x values and an infinite number of y values, even though we've only labeled 3 of them in each one. So just as we did before, domain is going to be the far left to the far right for this first one here. So it's going to be negative 2 all the way to what? 4. And the range is going to be bottom to top, so it's going to be what y value? Negative 3 all the way up to 2. And what you will notice over here, once I make it so you can see it again, what you will notice over here is it's just swapped. So now the domain over here is negative 3, 2, and the range over here is negative 2 to 4. You just switch the entire domain with the entire range. So this goes here, and this goes here. And of course, well, maybe not of course, I shouldn't say of course, but we could have started with this one and found this one. If I had given you that picture over there on the right to start with, we could have just easily turned it into the picture on the left. So you can go back and forth between the original and the inverse. Find the inverse of y equals 3x plus 4. Okay, I can do that. Done. How do you find an inverse, everyone?
Switch the x and y.
You switch the x and the y. Good. Now the problem is with this one, and it's not a huge problem, but they don't consider this simplified. They don't like this. So while this is the inverse, they want it simplified. In other words, they want me to solve it for y. So yes, this is the inverse. I have actually done what they asked me to do, but if they ask me to simplify it or they don't like this answer, then what I would have to do is I would have to subtract the 4 from both sides. And then I have to divide both sides by 3. I don't like writing it like that, so I'll write it like this. So technically, that is how they want you to write it. Even though, yes, we did what we were supposed to do, we swapped x and y, yeah, they want us to go ahead and solve it for y. So, inverses. Now, y equals 3x plus 4, and y equals x minus 4 over 3 are inverses of each other. Well, the domain and range is not very exciting for this one because these are both lines, and they're not horizontal lines or vertical lines. So both have domain and range of negative infinity to infinity. So what you're really doing is you're swapping negative infinity to infinity with negative infinity to infinity. So you're not going to notice anything really cool if you change the domain and range because they're identical. But here's what's cool about inverses, and here's what makes these inverses. I'm going to plug some numbers into this right here, and I can plug anything I want because it's a line. So I'm going to plug in, I don't know, I'll do -2, 0, and 5. I'm going to plug those 3 numbers in there. So each one of these numbers I'm going to multiply by -3 and add 4 to it. So -2 times 3 is -6, plus 4 is -2. That's interesting. Okay, if I put a 0 in there, I'll get a 4. If I put a 5 in there, I'll get a 19. Let's do one more -1. If I put in a -4, I'll get a -8. Now this is what makes inverses so cool, everyone, and this is one of the reasons we study them. Because if you come over to this one over here, and you plug in -2, 4, 19, and -8, do you know what you're going to get? Well, what I did was I just took these x values, turned them into y values, then I let these show up over here. And now watch this, everyone. -2 minus 4 is -6. Divided by 3, -2. What's 4 minus 4? 0. What's 0 divided by 3? 0. 19 minus 4? 15. 15 divided by 3? 5. -8 minus 4 is -12. -12 divided by 3? -4. So by switching x and y in the equation, we switch the x and y in infinite ordered pairs. And this will work for any single ordered pair you make. Any ordered pair you have for this first one here, the reversed is in this one over here, and vice versa. And vice versa. So, let me import some notes here. I wanted to make sure I had some good wording for this, so I actually typed this up ahead of time. All right. This is important, everyone. Well, hopefully everything I do in here is important. Every relation has an inverse because you can always swap x and y. I don't care what it is. If it's a graph, a list of ordered pairs, or an equation, you can always switch the places of x and y, no problem. Our big question is going to be this. is the relation a function that has an inverse that is also a function? We are concerned with functions. So what we want is we want a function before and after we swap x and y. That's what we want. We want a function both before and after we swap x and y. We want it to be a function when we get to it, and we want it to still be a function when we're done. So technically, everyone, we should never say the function does not have an inverse, because everything has an inverse because you can always swap x and y. But we may say that the function does not have an inverse that is also a function. That's the discrepancy, everyone, between saying the inverse is a function and the inverse is not a function, because there's always an inverse. We should never say the inverse does not exist, because the inverse always exists. But we may say the inverse does not exist as a function. Basically the same thing here, just two different wordings, everyone. Now here's the rub, and this is why I need to go over this in such detail. The math program, MyLab Math, or whatever they call it, is going to be sloppy, and they're going to use the terminology the inverse does not exist when they really mean the inverse exists but is not a function. So that's the problem, everyone. So when you see your math homework suggesting that the inverse does not exist, what they're really trying to say is that the inverse does exist, but the inverse is not a function. And so what happens is, if both the original and the inverse are both functions, then we call them one-to-one functions. If the original and inverse are both functions, then we call them both one-to-one functions. In other words, let me say it another way too. A one-to-one function is a function whose inverse is also a function. So I'm going to show you a quick little example of what I mean by this. Is that a function, everyone? Yes, it is. And in case you forgot why it is, it's because no x values repeat. That's something you learned back in our first unit. It's okay if you forgot that, as long as you remember it now. Yeah, that's a function. Okay. Is the inverse, which is 2, 1, 4, 3, 6, 5, also a function? Is the inverse also a function? Yes. Therefore, one, 2, 3, 4, 5, 6, 2, 1, 4, 3, and 6, 5 are both one-to-one functions. That's it. Since the original was a function and the inverse was a function, they are both the original and the inverse, are both one-to-one functions. Because what's a one-to-one function? A one-to-one function is a function whose inverse is also a function. All right. So now check this one out. Check this one out. And I'm not going to try and do any tricks today, just trying to make sure you all understand this. Is that a function? Do any x values repeat?
No.
No, so that's a function. That is a function. Yes. Is it a one-to-one function? No, because the inverse 3, 1, 3, 2, 5, 4 is not a function. Cool? Just want to make sure everyone gets this, because if you don't understand this, the basics here, then the rest of the section is going to be nonsense. So here is my big issue that I was trying to explain on the previous page. My lab math will say that the inverse of does not exist. The math homework is going to say the inverse of that does not exist. When really what they mean is the inverse is not a function. So you have to watch out for that when you're doing your homework, everyone. If they ever start saying the inverse doesn't exist, what they really mean is the inverse is not a function. So just be careful of that when you're doing your homework, and of course email me if you have any questions. Email Steve if this trips you up. Or use that Ask My Teacher feature and say, Steve, what were you saying about inverses not existing being the same thing as, just let me know what's up. All right. Questions or comments about that? Yeah.
So, would it be safe to say if you see any repeat?
Let me show you this. Little reminder here first. How do you know if your original relation is a function? If it's a list of ordered pairs, this is a function if no x values repeat with other x values. This is old news, everyone. I'm not saying it's something you all have memorized. It's old news, though, so this is something we've heard before. I just want you to have it in your notes again. Graph. A graph is a function if the graph passes the vertical line test, meaning no vertical line can be drawn and hit the graph at more than one point. That was how we decided if a graph was a function. An equation. In Math 121, we pretty much decided this, or I decided this and told you this. An equation is a function if there is no y to an even power and there are no plus minus symbols in the equation. So as long as you avoid having y to an even power, or you avoid that plus minus, which gives you kind of a choice, which is directly related to y to an even power, by the way, then we're pretty much going to say that we have a function. This is how you decide if your original relation is a function. This has nothing to do with inverses yet. That's just how you decide if your original is a function. Okay. But here is how we decide if the inverse to our original function is also a function. A list of ordered pairs. The inverse is a function if in the original function no y values repeat with other y values. So you can tell what's going to happen if you're about to swap the x's and y's, then those y's are about to become x's. So you want to see if any y values repeat. So if you look at your list of ordered pairs and no y values repeat, then your inverse is going to be a function. Otherwise it won't be. Graph. And we're going to practice these things, everyone. The inverse is a function if the graph of the original function passes what we call the horizontal line test. Brand new, everyone. This is the first time I've mentioned it. Horizontal line test. In other words, no horizontal line can be drawn to hit the graph at more than one point. This is actually the same thing as no repeated y values. Just one way is an ordered pair way of looking at it, the other way is a graphical way of looking at it. But these two ideas are connected. All right, now, what's the big question? Does our function have an inverse that is also a function? Here's a list that tells you that the inverse of a function equation is almost certainly not a function. There's an x to an even power. What's our simplest function that is x to an even power?
X squared.
X squared. The inverse is not a function because it fails the horizontal line test that we just learned about. The inverse of that is not a function. There's an x inside absolute value bars. These are functions, everyone, it's just that their inverse is not. There are multiple x-intercepts. There are intervals of both increasing and decreasing, or an interval of constant behavior. All of those things tell you that the inverse is not going to be a function. These tell you the inverse is not a function, not the original. I'm not suddenly saying these things are not functions anymore. What I'm saying is if you swap every x with every y, then you won't have a function anymore. If none of these four things above occur, then you might have a one-to-one function, but it can also be really hard to tell without a graph. I cannot possibly go through all the different types of functions up here that we have to worry about in your mathematical career. But I will tell you that in general, if you don't see one of these things happening, then there's a pretty good bet. There's a pretty good bet that you have a one-to-one function. Most equations that have only one x to an odd power one-to-one function, this includes all lines that are not horizontal or vertical. So, all lines except horizontal and vertical lines are one-to-one functions. All right. So, let's see what kind of damage we can do here. Everyone look at that, and no one say anything out loud, please. Everyone look at that, and no one say anything out loud. Because I'm going to ask a question, but I want you all to answer it for yourself, not for everyone else. And I want you to decide if that's a function, and then I want you to decide if it's a one-to-one function or not. So that's what I want you to be thinking about. So you kind of have three choices, everyone. You can either say, that's not a function, and that would be the end of it. You could say it's a function, but not one-to-one. Or you could say it is a one-to-one function. Those are kind of our three choices that we go through in our minds. Raise your hand if you think this is not a function. Raise your hand if you think it's a function, but it's not one-to-one. Raise your hand if you think it's a one-to-one function. Well, we're doing all right today. Very good. It is a function, but it's not a one-to-one function. And what our little verbal explanation for that is original is a function because no x repeats, but inverse is not a function because y repeats. That's it. That's why we know. And we can do the same thing with graphs. So for each one of these, we need to make a decision. We need to decide whether it's not a function but not one-to-one, or a one-to-one function. So this first one here, what do we think? What is this first one? You can just tell me this time.
It's a function.
It is a function. Is it also one-to-one?
No.
Here's why I think it is a one-to-one function, everyone, I'll tell you. I think it is a one-to-one function because, and I know we're just learning this, everyone, so it's okay if you didn't know, it passes the vertical line test and this new test that I just told you about called the horizontal line test. Does everyone agree that no vertical line could hit it more than once? Does everyone agree that also no horizontal line can hit it more than once? That's why this right here is a one-to-one function, because it passes both tests. How about this second one? Is that a function?
Yeah.
Yes. Is it one-to-one?
No.
No. It is a function because it passes the vertical line test, but it's not one-to-one because it fails the horizontal line test. In other words, I can draw a horizontal line and hit it in more than one spot. So that's still a function. That's our friend the parabola, everyone. It's still a function. It's just not considered a one-to-one function. What about the last one?
No function.
It's not a function. And here's what we'll do for this one. Not a function because fails vertical line test. Horizontal line test is not even used because once we know it's not a function, we don't really bother with it anymore. So we don't even use the horizontal line test. So here's a summary for everyone that I typed up ahead of time. I did a little bit of typing before class today. I got nervous because I always want to make sure I get through this stuff for you. When do I, the mathematician, use the horizontal line test? Well, there are three classifications that may come up. Not a function. The graph failed the vertical line test and is not a function. The horizontal line test is not used. That was the third example we just did up there. Failed the vertical line test, so we were done. A function, but not one-to-one. Graph passed the vertical line test, but failed the horizontal line test. That was our second example. The original was a function, but then the inverse would not be. A one-to-one function. Graph passed the vertical line test first, and then passed the horizontal line test second. And that was the first example above. So those are the situations where you use the vertical line test and the horizontal line test. All right. Let's see here. We already know that an inverse is found by swapping every x and y in every ordered pair. This also swaps the entire domain with the entire range. And here's something new. The inverse of a graph is actually the reflection of that graph over the line y equals x. I'll show you an example of that, don't worry. The inverse of a graph is actually a reflection over the line y equals x. So that's another way to think about it. Yes, you can say every x and y is switched. But you can also say when looking at a graph, what's happened is the graph is actually reflected over the line y equals x. May I show you an example of this? All right, let me summon up my example here. All right, here we have a graph, and what happens is I'm going to say, and I want to see if you agree with me, that this is a one-to-one function. Does everyone agree that that passes both the vertical and horizontal line test? All right, so that is a one-to-one function. Now, let's go ahead and draw the inverse of that. I think to do the inverse, I'm going to need some ordered pairs here. So I'm going to have -8, -3. I'm going to have -2, -1, 1, 4, and 8, 6. If I know those four ordered pairs, do I also know four ordered pairs for the inverse?
Yes.
Yes, I do. And they are going to be, let's see here, -3, -8, -1, -2, 4, 1, and 6, 8. 6, 8, 4, 1, -1, -2, and -3, -8. And I do my best to make some straight lines. Now that's the inverse, but check this out, everyone. Just so it doesn't get too crowded, I think I'll draw the original one over here. So the original one, once again, has its ordered pairs at -8, -3, -2, -1, 1, 4, and 8, 6. Man, I could get turned around doing this. And here comes the line y equals x. Everyone see the reflection? Yeah, it's just like it spun around it. It spun around it. Okay. So how about we have you try one? How about we have you try one of these? So I'll bring one up here. This one, we'll do this one here. Very similar to the one we just did, just new problem for you. So what I'd like you to do, everyone, is I'd like you on one coordinate system to draw the original, the inverse, and that line y equals x. So you're looking at your original function. It's got four labeled ordered pairs. You swap the order of those four ordered pairs to get four new ordered pairs. So -9, 7 becomes 7, -9. 0, 4 becomes 4, 0. 2, -8 becomes -8, 2. And 9, -9 becomes -9, 9. Then you just connect those dots as well. And then if you draw in the line y equals x, that perfect diagonal line going right through the origin, you should see that it's reflection. It looks like one of them just swiveled around that line. Kind of like it was anchored to it and just twisted around, three-dimensional, 180 degrees. Not only that, but we can write down the domain and range of both the original and the inverse. And what's cool about this, everyone, is you can actually just do it by looking at the original. The original has a domain of -9 to 9 and a range of -9 to 7. But you don't even need to make your new picture Because if you just swap the order of those domain and ranges, the domain on the inverse is -9 to 7, and the range is -9 to 9. Why? Because the domain and range swap along with every single other ordered pair on the graph. So, class, can we sketch an inverse without ordered pairs? Well, we can. We can because, look at this, everyone. Here we have some function. Now I know this is a function, everyone, because it passes the vertical line test. I know it's a one-to-one function because it also passes the horizontal line test. And the way I've drawn this, it should look sort of like a piece of a rational function, but it is still just a function. But if I look at this thing, I can say that the domain of this is going to be -infinity to 0, and the range is going to be 0 to infinity. If you look at it, you'll see it goes left forever, but never gets up to the y-axis. That's why we got the domain. And it starts just barely above the x-axis and goes up to infinity. That's why the range is 0 to infinity. Now right here is the line y equals x. So what we want to think about is we want to think what would happen if we suddenly just flipped that over that line. What would we get? Do you think that could be the inverse down there? Does it look like a reflection over that line? It does to me. Let's double check our domain and range. This one seems to go from 0 to infinity for the domain, and from -infinity to 0 with the range. Once again, the domain and range are swapped. So even though I didn't have any ordered pairs on this one, just by looking at the graph, I was able to reflect it over the axis. The line y equals x. All right. Let's do one more thing here, then we'll take a break. Give the inverse equation for y equals 2x plus 6. Everyone, if I'm supposed to give the inverse of that, what's the most important thing to do?
Swap x and y.
Swap x and y. So, this is basically a correct answer, everyone. Swapping x and y. That is basically all you have to do. Are they going to like this answer, do you think?
No.
No, they want you to solve it for y. Which we can actually do in 2 steps. What are our 2 steps? To solve for y, get y all by itself. Yeah, well, first move the 6, then we'll divide by 2. We actually could divide by the 2 first. But in this case, I think it's easier to subtract the 6 from both sides and then divide both sides by 2. Okay, that's our inverse. Now, what would happen if we were given something like this? F of x equals 3x minus 9. Well, okay, no big deal. There's no y there. There's no y there. So what I'll do is I'll just change f of x to y. Now I can swap x and y. Does that look okay to everyone? Yeah, if they give you function notation instead, don't let that spook you. Just get rid of that function notation, put a y in there instead. So now my inverse is x equals 3y minus 9. No one's going to like that. So what should I do? Add 9 to both sides. And divide both sides by 3. And then we can say our answer like this. Y equals x plus 9 over 3 is the inverse of f of x equals 3x minus 9, the original equation we started with.
And should you simplify the first equation further? Or no, you can't, because the x normal.
No, we could write it as x over 3 plus 3. This would actually also be correct. That would actually be all right to write it like that, but we don't need to do that.
Okay.
Now, here's the thing, everyone, and then we'll take a break. I just want to make sure we get this point out there first. It seems like in math, with all the symbols and all the notation we use, there should be a way to tell people that these two functions are inverses of each other without writing the words is the inverse of. So here's what we're going to do, everyone. F of x equals 3x minus 9. And as we know, we pronounce that f of x. And here's what we're going to do. What it looks like I've done, everyone, just so you know, is it looks like I wrote f of x, but it looks like I put a power of -1 on the f. That's what that looks like. It looks like an exponent of -1 on the f. And this is read aloud as f inverse of x. And this is a way of telling people that we know, the mathematicians, we know that these two functions are inverses of each other. They're not just any two functions. They are inverses of each other. In other words, if the ordered pair AB is on f of x, then BA is on f inverse of x. We're telling people that we know that every single ordered pair on one of them has the swapped version on the other one. And so we write this, f inverse of x. F inverse of x means the inverse function of f of x. Only works for one-to-one functions because we are using function notation. And I know -1 power usually means put it on the bottom, but that's not what it means in this case. That does not mean put it on the bottom. What it means is that is the inverse. And everyone, that is where we will take our break. Sorry, I went a little bit long. So I will see. While we're at break, I put this up on the board. This is how we find the equation of the inverse function from the original function equation. We've done this. We did this already. We just did it right before the break, but here are the steps. Replace the function notation with y. If there's an f of x, change it to a y. Then, once you've done that, change every y to an x and every x to a y. The reason I phrase it like that is because some of the equations we're going to look at, maybe just one today, there's going to be multiple x's that have to both become y's when we change x with y. Then you have to solve for y. That's usually the hardest step, and we're going to do a couple today where that's a little bit tricky. And then we're going to change the appropriate inverse function notation. In other words, if you started with f of x, you use f inverse of x. If you started with g of x, you use g inverse of x, and so on. So you need to make sure that you're using the right function notation. And just a reminder to everyone, please remember that when you see that f inverse of x notation, that does not mean 1 over x. I know that's what a -1 power usually means, but it doesn't mean it in this case. And it's read aloud as f inverse of x, not f to the negative 1 power. F inverse of x. Where have we heard inverse before? Where have we heard inverse before today? Does anyone remember? Back when we looked at our basic functions? Did I ever use the term inverse back then? Does anyone remember what the inverse of f of x equals x cubed is?
Cube root of x.
Cube root of x, good. Yep. Those are inverses of each other. And now I can say they're inverses by using this inverse notation. I don't just need to say they're inverses of each other. By the way, there's no rule about which one's the original and which one's the inverse. You could just as easily have said this, that you're starting with the cube root of x, and that the inverse of that is x cubed. It's not like one's more important and the other one is its lowly little inverse there. They're both equally important. They both have equal rights to be called the original, and both have equal rights to be called the inverse. So it doesn't matter which one you do. All right. But our equations can get more complicated than that. So we'll say this. H of x equals the cube root of 5x minus 3. Find h inverse of x. Find the inverse function. Okay, so we want to find the inverse function of that. First of all, we have to change the function notation to y. And if you're thinking that first step is easy, that's what I want you to think. If you're thinking it's hard, let me help you with it, or let Rachel help you with it so you can see that it is easy. You're just changing the function notation to a y. That's it. The second step I also want you to feel that you can do pretty quickly when you just write the whole thing again, but you just change the y to an x and the x to a y. And that's actually the inverse right there. That's the most important step. Unfortunately, it's not where we get to call it quits. Because now what we need to do is we need to solve for y. And how do I want to say this? I want to say you work from the outside in. So in other words, if I'm going to try and solve this for y, I'm going to kind of work from the outside in. So you'll notice that on the right side of the equation, the thing that's over everything is that cube root. Does everyone see that cube root there over everything? So the first thing we're going to do is we're going to cube both sides. And if you cube both sides, it's going to look a whole lot better. Because now it becomes x cubed equals 5y minus 3. What's our rule? If you do it to one side, do it to the other side, right? So I'm just going to cube both sides. Now we are actually only 2 steps away from solving for y. Because whether this is an x cubed or whether it was an x or an x to the 5th or whatever, what's our next step to get y by itself? What will we do next? Add 3. Add 3 to both sides of the equation. And then what's our final step? Divide by 5. Okay. And that was step 3 in the whole process. And step 4 is a fast step, but we do need to remember to do it. Step 4 is to change back to function notation, but use the inverse notation. So what was my original function called? H of x. So my inverse is going to be h inverse of x. So, class, what's interesting about this is there's actually not supposed to be a big mystery to how these inverses work. An inverse function does the opposite operations in the opposite order of the original. This is actually one of my favorite things to talk about when I'm talking about inverses, everyone. I think this is really, really cool how they work. What an inverse actually does is it does the opposite operations in the opposite order. So here's what I want everyone to do with me right now. I want you to look at this h of x equation. And I want you to think about plugging a number in there. I actually don't care what number you plug in there, but I want you to think about plugging a number into this h of x equation. What's the first thing you would do to that number when you were trying to crunch out a y value? What's the first thing you would do to that number?
Multiply by 5.
First thing you do is you multiply by 5. Everyone cool with that? After you multiply your number by 5, what would you do next?
Subtract 3.
You'd subtract 3. Everyone with that? You'd subtract 3. Then what would you do? What's that?
Cube it.
Not cube it,
Cube root it.
cube root it. All right, everyone, so let's plug a number in there. Let's plug a number in there and do those things. So if we plug in 3, no, I don't want to plug in 3. I want to plug in 6, sorry. Let's plug in 6. Just like we were told. 5 times 6, everyone? 30. 30 minus 3? 27. Does anyone know the cube root of 27 off the top of their head?
9.
Careful. Cube root of 27 is 3. So this will become 30 minus 3. You're doing fine. Don't worry about it. 27 equals 3, so we get the ordered pair, 6, 3. Now watch this over here, everyone. Go to the inverse one. Let's say we were going to plug a number into the inverse function. What's the first thing we would do? If you plug the number in here for x, what's the first thing you do to it?
Cube it.
You would cube it. Then what would you do?
That's 3.
Add 3. Then what would you do?
Divide.
Divide by 5. If we were to plug a 3 in here, then we would get 3 cubed is 3, plus 3 is 30, and 30 divided by 5 is 6. Now I picked numbers that would work out nicely, but that's going to happen for every single number you plug in. You can always go back to where you came from. That's what the inverse does. I don't care what ordered pair you plug in here. If you were to plug some number into the original function, you got some other number out, and then you would plug that number back into the inverse, you would get back to where you started every time. It's just easy to see with numbers that are not nasty decimals. But this is what I mean. I think this is really neat, everyone. Multiply by 5, subtract 3, take the cube root, cube it, add 3, divide by 5. They're the exact opposite in the exact opposite order. And that's how every inverse works. All right. They get harder? Yeah, they get harder. It's nice that someone's telling us that, yeah, that is a one-to-one function. That way we know that there is an inverse and it's a function. The inverse is a function. All right. And I do want you to truly believe that the first 2 steps of finding the inverse are easy. What's the first step in finding the inverse? Change f of x to y. What's the second step?
Switch.
Switch the x and the y. This is where it's okay to slow down a bit, because this is where it's different for every problem. The first 2 steps are always the same. Change the function notation to y, switch x and y. But now's when it gets trickier. Why is it tricky? Because there's a stupid fraction. So let's get rid of the fraction. the way you get rid of a fraction like this is you multiply both sides of the equation by that denominator. If you multiply both sides of that equation by that denominator, then you're going to get x times y plus 3 on the left side and just a 1 on this side. Okay. Now, from this point, I actually have seen two really good ways to finish this. I don't want you to think there's only one way to solve this for y. But that is what we're doing, everyone, is we're solving it for y. So does anyone have an idea of what we should do next?
Add 1 both sides.
Say again, sorry?
Add 1 both sides.
Add 1 to both sides? No, we want to get y by itself. Maybe I just misheard you. I apologize if I did. How do we get y by itself? What should we move over to the other side? What do we want over there? Oh, divide by x. Maybe that's what you said. I'm sorry if I didn't hear you right. Yeah, we'll divide both sides by x, and we'll get y plus 3 equals 1 over x. Now what?
Move the 3.
Move the 3. Very good. Subtract 3. That means nth inverse of x equals 1 over x minus 3. How was that? Here's something that I used to do. I would distribute the x and subtract 3x from both sides. And then I divide both sides by x. So my question to you is which one's right? 1 over x minus 3 or 1 minus 3x over x? They're both right. They're identical answers. They're identical answers, so it doesn't matter which one, whichever one you were more comfortable with. I wanted to show you this example, though, because this is a slightly more complicated solving for y problem. All right. What if someone claims to have already found the inverse? Now let me do it like this. This will make it less confusing. Claim g of x equals x minus 9 over 12 is the inverse. All right, this is a big deal. I know a lot of people struggle with this part, so this is another bump in our road through inverses, this next example here. Here's the idea, everyone. An inverse is supposed to undo what the original function did. So in other words, it should be the case, everyone, that if I plug a number into this guy right here, like 2, 12 times 2 plus 9 equals 24 plus 9 equals 33, then it should be the case that if I plug 33 in here, I get back to 2. So I actually believe these are inverses of each other, but here's the problem. 1 or 100 ordered pairs does not prove inverse because it must work for every ordered pair. Now, class, since I picked that number at random, I'm pretty convinced this is an inverse. They are inverses of each other. I'm pretty convinced they are because the chances that I would pick a number at random and 2 would become 33 and then 33 would go back to 2 is pretty slim. But the problem is, one example does not prove it. Any more than if you went outside one day in Colorado and it was raining and you said, oh, it's raining today, it must rain every day in Colorado. One example, even 10 examples. If you went out in Colorado 10 days in a row and it was raining every single day, could you make the statement it rains every day in Colorado? No, you need to prove it. And here's how you prove it. Prove f of x and g of x are inverses of each other by showing f composed with g of x and g composed with f of x both simplify to x. The way you prove two functions are inverses of each other is you compose them. And after you compose them, you simplify that composition. And if that composition simplifies down to a single x, then they're inverses of each other. This is how you have to prove it. Yes, I would believe that you were right if you showed me it worked for 20 ordered pairs, but that doesn't actually prove it. By the way, this is not my idea. This is right here. Let f be a one-to-one function, then g is the inverse function of f if, when you compose them, it simplifies down to x. So would you like to see that work? Let me show it to you. All right, I'll just repeat the example down here. So we were saying f of x equals 12x plus 9, and g of x equals x minus 9 over 2. I know we haven't done this in a while, so bear with me here. F composed with g of x is the same thing as f of g of x, putting the g function inside the f function. That would mean x minus 9 over 2 gets plugged into the f function everywhere we see an x. That means this becomes 12. Did I write this right? No, that should be a 12 up there. I was about to say, this isn't going to work. Everyone, I copied it down wrong from upstairs. It's supposed to be a 12 in the denominator. I just wrote a 2. So make sure you have 12 down there. I was about to say, this isn't going to work at all. I almost blew the whole math right there. So you plug that in there. Now the good news is the simplifying should almost look like it just happens automatically. For instance, here we have a 12 times a fraction with a 12 in the denominator. Will those 12s cancel? Yeah, they sure will. So you're going to have 12 times x minus 9 over 12 plus 9, and the 12s will cancel, and you get x minus 9 plus 9. What does that simplify to? X. Let f be a one-to-one function, then g is the inverse function if f composed with g of x simplifies to x, and g composed with f of x simplifies to just x. Is this what I wanted to have happen? Look at that, everyone. When I plugged one function into another function, it simplified down to an x. I realize you have not done compositions in a while. So you might have to go back and look at your notes for compositions, but this is how this works. You plug one function into another function, and you simplify. It's the curse of math, everyone. It keeps building on itself. You compose the other way. G composed with f means g of f of x means put 12x plus 9 into the g function. That's going to look like this. The 9s on the top will cancel each other out. You'll end up with 12x over 12, which equals x. Since g of x is the inverse of f of x equals 12x plus 9, we can rename g of x as f inverse of x equals x minus 9 over 12. All right.
Well, couldn't we just skip all that and just do the math to switch the equation?
You mean notice that this does the opposite operations in the opposite order?
Yeah.
Yeah, in general you can do that, but that's sometimes difficult with more complicated functions. Something like this. When there's multiple x's, it can be very, very hard to figure out what the opposite operation in the opposite order is. It's an amazing question. And it's what I would do also, is I would just run through the math in my head, but we can't always do that. So let's try this one here. Now I'm going to find the inverse of this function, everyone. And once again, I don't want you to believe that the first two steps are hard, because they don't have to be. What's the first step to finding the inverse?
For y and f.
Just change that to a y. Is everyone cool with that? Very quick. Very quick. But here, for the first time, on step 2, I want you to notice that both x's become y. Because there were two x's in the equation, they both have to become y. This is about as hard as these finding the inverse problems get. What makes that look so hard, everyone? The fraction. Does the fraction bother you? Should we get rid of the fraction? Okay, here's how we get rid of the fraction. Yeah, the two y's is also hard. I heard someone say that. That's absolutely going to be frustrating. But the first thing I can do is I can get rid of that fraction. And that's just going to make this a lot nicer. It's not my job just to do this problem as fast as I can. My job is to do this in such a way that you can remember how to do it also and practice it later. So I think it's a natural thing to want to get rid of the fractions. All right, so let's write that down just so we remember what we did. We kill the fraction. What's that?
Is it supposed to be 1 minus y?
Oh, I hate what I do. You're awesome, thank you.
Well, I was Rachel, that sounds.
That was just me. I was like, oh my god.
No, it wasn't just you. Everyone's smart. What is going on? You know what? I've had it. Okay, 1 minus y. So now it is x times 1 minus y equals 4y plus 3. Checking my notes, making sure that I've got that all fixed. X times 1 minus y, 4y plus 3. Okay, we're good. Thank you very much. Thank you for pointing out before I got to the end. All right, now, what's the next natural thing you want to get rid of? You want to get rid of the parentheses? Let's get rid of the parentheses. So that means that x times 1 minus y equals 4y plus 3 is going to become x minus xy, distribute the x, 4y plus 3. So kill parentheses. So violent. Kill the parentheses. Now let's take a step back and remember what we're trying to do. What are we trying to do? We're trying to solve for y. So here's what we'll do. Use adding and or subtracting to get every term with y on one side and every term without y on the other. There are some things that have y's in them, some things that don't. So what we'll do is we'll get everything with a y on one side and everything without a y on the other side. So, class, see if you follow this. I'm going to take my x minus xy equals 4y plus 3. And I'm going to add xy to both sides. And I'm going to subtract 3 from both sides. Now, if I do that, everyone, I will end up with x minus 3 on the left, and I will end up with 4y plus xy on the right. Everyone see that? Get everything with a y on one side, everything without a y on the other side. Why is that natural? I think it's natural because we're trying to get y by itself. All right. Now, the reason you would do that is now you can factor out y and divide by the leftover garbage. I should write a math book. I factor out a y. You know what's so cool about factoring out a y? What was once 2 y's now is 1 y. Divide by the leftover garbage. And we're done. The original was f of x. So therefore, f inverse of x is x minus 3 over 4 plus x, or x minus 3 over x plus 4, if you prefer. That 4 plus x looks kind of nasty on the bottom, so I changed it to x plus 4. Not required, just makes it look better to me. Class, that's about the hardest type of problem you have to do in this section. And why is it hard? Because that stupid third step. That third step where you have to solve that for y, or solve it for y. And I know you've solved equations for things before, but we haven't done much of that in this class. So basically the idea is this, everyone. We think we're right. We think that f of x equals 4x plus 3 over 1 minus x has inverse x minus 3 over x plus 4. And I'll tell you, class, I'm going to be straight up with you about this. You really don't have to do both of those. You really don't have to do both of them. You do have to compose to see if one's the inverse of the other. That is how you figure out if one's the inverse of the other. But I'll tell you, class, if one works, the other one's going to work also. So it's really not important to do both. But we do have to do one to show that this is this. And your question before was awesome about can't we just kind of look at it? But we can see from this example that you really can't just look at it and see if it works. So we are going to verify, everyone, that one of these is the inverse of the other one. And this is going to look like crap, because look what I have to do. I have to do this. F of g of x equals 4, or let me put it in 2 steps here. Let me do it in 2 steps. Because this am I doing that wrong? Sorry. What is that supposed to simplify to? Anyone? Not the, well, when you're doing an inverse, when you're proving inverses, it's supposed to simplify to the same thing every time. That's okay, we just learned it. If you have an inverse and you compose them, what is it supposed to simplify down to?
X.
Just x. That's how you make sure it's an inverse. You plug one in function into the other one, you go through all the nightmare of simplifying it, and you're hoping to just get an x at the end. And if you get just an x at the end, they are indeed inverses of each other, and you've won. Well, I don't want to do this, but I'm going to. And once again, I hate fractions within fractions, so watch what I'm going to do. I'm going to multiply both the top and the bottom of this thing by x plus 4. Now be careful when you do this, everyone, because here's what's going to happen. This x plus 4 is going to distribute to that and that, and down here it's going to distribute to that and that. So if you do that, everyone, here's what you're going to end up with. You're going to end up with 4 times x minus 3, because the x plus 4s are going to cancel in that first term. The next one is going to be minus 3 times x plus 4, because it's going to pick up the x plus 4. This one's going to become x plus 4, because 1 times x plus 4. And this one, they're going to cancel. This is what happens when you multiply by that denominator, x plus 4 over x plus 4. Cancels there, and it cancels there. But it shows up here, and it shows up here. And just so you know, everyone, that 1 right there did not go away. It's actually in front here, but I didn't bother to write it because 1 times anything is just itself. Then we clean this up. 4x minus 12 minus 3x minus 12. I hate everything. Okay, let's see what happens. And then here I get x plus 4.
It's x plus 3 on the top.
Say again?
It's x plus 3 on the top for some function, so it's x plus 3 and x plus 4.
You're absolutely right. I'm just angry with myself. I should stop trying to go off book. Holy cow. Thank you. Who said that? Thank you. All right. Yes, it was 4x plus 3 in the original function. Okay. Anyway, now that all the finesse and joy of this problem is gone, what does the top simplify to? Do the 12s go away on top?
Yep.
And what's 4x plus 3x? 7x. Do the x's go away on the bottom? And what's 4 plus 3? Hooray. I lost my spirit. All right, everyone. Yes, that is what happens. So there is probably one of the trickiest problems you'll see in this section is finding an inverse in an equation that has 2 x's in it and then proving that they're inverses by doing a composition. Since f composed with g of x equals x, the functions are inverses. Okay, let me close today with a couple comments here in the last 7 or 8 minutes. I got a couple more things I want to say. F of x equals 1 over x. Find the inverse function. First step, everyone. Change it to a y. What's the second step?
Swap.
Swap x and y. That's actually the most important step you will do. What's the third and hardest step?
Isolate y.
Isolate y. How do you want to isolate y? What do you want to do? What do I usually do on these problems if there's a fraction?
Multiply it, cancel out the denominator.
I get rid of the fraction first. Does everyone agree with that? That's what I've been doing. I get rid of the fraction first. So if I multiply both sides by y, let me do that on another step, sorry, so you don't have your notes such a mess. Feel so defeated. All right. Gives me x times y equals 1. Now what do? Divide by x. Fourth step. What gives? It's the inverse of itself, everyone.
That's just how the equation is, though.
Here, I'll show you. It's pretty sweet. Watch this, everyone. You plug a 2 in there, you get 1/2. You plug 1/2 in there, you get a 2. It's actually its own inverse. Did you know there's actually an infinite number of functions that are their own inverses?
Really?
Yep, that's right. Any line with a slope of -1 is its own inverse, any line. What does a line with a slope of -1 look like? It looks like this. Negative x, someone give me any number, any real number.
73.
I heard 1, but I also like 73 a little better for this example. Okay, change that to y. Swap x and y. Let's see here, subtract 73 from both sides. Does that solve for y yet?
No, we have to remove the negative on
I have to multiply both sides by -1 or divide both sides by -1. So if I multiply both sides by -1, that will give me negative x plus 73 equals y. That's kind of cool. Finally, how do we know a function's not one-to-one? Can someone tell me why they know that function's not one-to-one?
y. You said earlier that if, for the most part, if it's an even power, it's not going to be a 1-to-1.
Good. Who can tell me another way you know that's not one-to-one? Yeah,
It fails the horizontal line.
very good. Very good. Here's another way you can tell. What do I get if I plug a 2 into that function, everyone? 7. What do I get if I plug a -2 into that function?
Negative 7.
You still get a 7. That means it has the ordered pairs. Has ordered pairs with repeated y's. That's 3 ways you can tell this one is not a function. I'm sorry, yeah, not a one-to-one function. It's still a function, it's not one-to-one. Now, class. That is absolutely 100% not true. You cannot say that f of x equals x squared and f inverse of x equals the square root of x, because it is not the case. I know this is not the case because this is not one-to-one. I also know it's the case because this graph looks like this, and this graph looks like this. They are not reflections of each other. X squared and the square root of x are not inverses of each other because their graphs are not reflections of each other over the line y equals x. And this one has the ordered pair -3, 9, for instance, but this one does not have the order pair 9, -3. Because you can't take a square root and get a negative answer. This one has a domain of -infinity to infinity, and this one has a range of 0 to infinity, while this one has a domain and range of 0 to infinity. Now, after I gather my thoughts, we might want to do a little bit more in this section next time before we move on to section 4.2, but there's no reason you shouldn't be able to do most of the homework for this. Sorry I made a couple mistakes today.